All right, we are in chapter 10, section 6. Let's warm up a little bit. Find the exact value. Sine of 30 is going to be the 30, 60, 90 triangle, which we have right there. Sine is opposite over hypotenuse, so that is equal to 1/2. Cosine pi over 4. Pi over 4 is the 45, 45, 90 degree triangle. That's 1 square root 2. Cosine is adjacent over hypotenuse, which is 1 over root 2, which you need to rationalize. Root 2 over 2. Tan 60. 30, 60, 90 triangle. 1 square root square root 3, sorry. And 2. Tan 60 is this one, opposite over adjacent, so square root 3. And tan 45, 45, 45, 90, opposite over adjacent is 1. All right, a ladder leaning against a building makes a 75-degree angle with the ground. The bottom of the ladder is 3 feet from the base of the building. Feet. How high up the building is the top of the ladder? So we have x. I have opposite over adjacent, so we can say tan of 75 equals opposite over adjacent, x over 3. So 3 times tan 75 equals x. X equals 11.2 feet. All right, the meat of this lesson. So in this lesson, you will study formulas that allow you to evaluate trig functions of the sum or difference of two angles. So we have sum and difference formulas. All of our sum formulas for sine, cosine, and tangent, and all of our difference formulas. Basically, we're going to take a crazy angle like 75 and change it into two angles that we know. Let's see, 75, if I subtract 45, yep, 75 is the same as 30 and 45, which we know angles for. Sorry, we know given triangles are triangles for those angles. We need to make sure that we realize that sine of a plus b is not equal to sine a plus sine b. And everything else, cosine, tangent, etc. So what we want to do is, for instance, change something like sine 75. If we're trying to find an exact value, we would change that into sine of 30 plus 45, and then use this formula for it. Okay, sine of 30 cosine of 45 plus cosine of 30 sine of 45. And we'd use our triangles to figure out all of those values, right? Okay, let's try it. First, we're going to find the exact value of sine 15. When I say exact value and something crazy like 15, I don't have a triangle for 15. So I need to use one of my formulas to do that. Okay, 15 is a small number, so I know if I have a 5 around there, I'm going to have to use 45 in addition or subtraction. I can figure that sine of 15 is the same as sine of 60 minus 45, right? So I have 60 is A and 45 is B. So let's use that formula on the previous slide. I have sine of 60, cosine of 45, minus cosine of 60, sine of 45. If you go to your triangles, you have a cheat sheet for sine of 60 is the same as square root 3 over 2. Cosine of 45 is square root 2 over 2. Minus cosine 60, sine 45. This gives me square root 6 over 2. No, I'm multiplying over 4, sorry. Minus square root 2 over 4. That gives me square root 6 minus square root 2 over 4. This is an exact answer, which is exactly what I'm looking for. Let's try B. Tan of 7 pi over 12. These are a little bit harder because they're in radians. But I know that my triangles are 30, 60, 90, which is pi over 3, and pi over 6, and then 45, 45, 90, which is pi over 4. So 7 pi over 12, I can say, is the same as pi over 3 plus pi over 4. Because if I get a common denominator, 3 goes into 12 4 times, and 4 goes into 12 3 times. So these right here are the same as that. But I'm actually going to use these in its simplest form. So it's a sum rule. So we have tan of 7 pi over 12 is the same as tan of 3 pi, pi over 3 plus pi over 4. Let's go ahead and use that sum rule. Tan pi over 3 plus tan pi over 4 over 1 minus tan pi over 3 times tan pi over 4. Okay, use our special triangles. Tan pi over 3 is square root 3. Tan pi over 4 is 1 over 1 minus square root 3 times 1. Okay, let's see. I'm going to grab this and go to a new slide. Okay, this one's harder to rationalize. I have square root 3 plus 1 over 1 minus square root 3. Okay, I'm going to go ahead and multiply that by 1 plus square root 3. Do you remember that complex conjugate pair? Okay, that means I'm going to FOIL. Yay! But in the denominator, my middle term is going to cancel out. So I'm going to do first, which is 1, outer, positive root 3, inner, negative root 3, and last, minus square root of 9, which is 3. So this is all over 1 minus 3, which is negative 2. Here we have first, square root 3, outer, inner, and last. First, yep. Outer is not right. I knew there was something wrong here. Okay. Let's fix our mistake together. First times first is square root 3. Check. Outer is square root 3 times square root 3, which is square root 9, which is just plain old 3. Inner is 1, and last is square root 3. That gives me 4 plus 2 root 3. I can actually take a 2 out of that over negative 2. So that is negative 2 plus root 3, or negative 2 minus root 3. Okay, the key here is I had to rationalize my denominator by multiplying by the complex conjugate pair. All right, this one is a tad bit more difficult. So we're going to find cosine A minus B, given that cosine A is negative 4/5 within this range, and sine B is 5/13 within this range. So if I'm in my, well, let's do this. my coordinate plane. Pi to pi over 3 pi over 2 is actually in here. And 0 to pi over 2 is in this quadrant. Right, so if I draw my triangle down here, this being angle A, I know cosine is adjacent over hypotenuse. And if I use the Pythagorean theorem, a squared plus b squared equals c squared, I get -3 for that side. So cosine A is -4/5, and sine A is -3/5. Cool? Now, B is in here. This is B. I know sine is adjacent over hypotenuse, so is opposite, so katoa is opposite over hypotenuse. So 5/13, Pythagorean theorem, a squared plus b squared equals c squared. Let's see, subtract 25. Square root of 144 is 12. Everything here is positive, therefore we can say that sine B is 5/13, and cosine B is, adjacent over hypotenuse, 12/13. Cool? So we're going to find cosine A minus B, because our formula for that is, this is why we had to find everything. I guess I could have told you that. Cosine A, cosine B plus sine A, sine B. So cosine A is -4/5. Cosine B, forgot the S, is 12/13. Sine A, -3/5. Sine B, 5/13. Okay, do the math here. I get -63/65. That's my answer. I know, crazy. Okay, good job. All right, now we're practicing a little bit, right? So find the exact value of the expression. What is 105? Well, I know there's a 45 in there somewhere. So if I take 105 minus 45, I get 60. So 105 equals 60 plus 45. I need to go back to my formula. Sorry, I have sine of 105 is the same as sine of 60 plus 45, which is the same as sine of 60, cosine 45 plus cosine of 60, sine of 45. Sine A, cosine B, cosine A, sine B. So sine of 60. If you look at your special triangles, sine of 60, opposite over hypotenuse, square root 3/2. Cosine 45 is, adjacent over hypotenuse, 1 over the square root of 2. We'll rationalize it later, okay? Cosine 60, adjacent over hypotenuse, 1/2. That should be a 1. Sine 45 is opposite over hypotenuse, 1 over root 2. Okay, that gives me, multiply across, square root 3/2 root 2 plus 1 over 2 root 2 is 1 plus root 3/2 root 2. You know, I am going to actually rationalize those first, because that's how my head works. So I'm going to multiply this one by root 2 over root 2. And this one by root 2 over root 2. You can do it later. I know you can. This gives me square root 6 over 4. Square root 2 over 4. So square root 6 plus square root 2 over 4. All right, this one I actually have on the next page. Cosine 75. Again, when I see a 5, I think, oh, I don't know what it is, but there has to be a 45-degree angle in there somewhere. So cosine 75, 75 is actually equal to 45 plus 30, right? So cosine 75, I'm going to go back to that formula. So we actually have cosine 45 plus 30. Okay, cosine A and B, that gives me cosine 45, cosine 30, minus sine 45, sine 30. Okay, go back to our special triangles. And I know that cosine 45 is adjacent over hypotenuse, 1 over root 2. Cosine 30, so adjacent over hypotenuse, square root 3 over 2. Minus sine 45, so is opposite over hypotenuse, 1 over root 2, times sine 30, opposite over hypotenuse, 1/2. Okay, multiply this, I get square root 3 over 2 root 2 minus 1 over 2 root 2. Multiply by root 2 over root 2. Multiply by root 2 over root 2. The numerator on the left gives me root 6 over 4 minus root 2 over 4. So I get root 6 minus root 2 over 4, which is the correct answer. Still practicing. Yep, these are the harder ones, right? I know that my options here are pi over 3, pi over 6, and pi over 4. So if I make all of these 12, 4 pi over 12, 2 pi over 12, and 3 pi over 12. So how do I get to 5? It looks like 2 pi over 12 plus 3 pi over 12 will give me 5. So really here I have tan 2 pi over 12 plus 3 pi over 12. But I don't really use those numbers. So what I'm going to use is pi over 6 plus pi over 4. Okay, that's the hard part about that one, right? So let's go to our formula. Sorry, I keep having to grab it because I didn't bring my textbook home, but that's okay. There we are. So the sum formula for tangent is tan A plus tan B all over 1 minus tan A tan B. All right, go to your special triangles, figure everything out. Tan of pi over 6. Pi over 6 is actually 30 degrees. Pi over 4 is 45 degrees. So tan of 30 is opposite over adjacent. So I have 1 over square root 3 plus tan of pi over 4 opposite over adjacent. 1 over 1 minus tan of pi over 6, 1 over root 3 times tan of pi over 4, which is 1. That gives me 1 over root 3 plus 1 over 1 minus 1 over root 3. Okay, I'm going to take that and start a new slide so I can finish it. So I had, first I'm going to rationalize those funky fractions, okay? Remember, I can multiply it by anything as long as it is the equivalent to a 1. So that gives me root 3 over 3 plus 1 over 1 minus root 3 over 3. Cool? All right, I'm going to multiply this by the complex conjugate pair of the denominator, 1 plus root 3 over 3. Okay, this is sort of messy, right? It'll be okay though. Let's hit the denominator first. FOIL. First is 1, okay, outer, root 3 over 3, inner, minus root 3 over 3, and last. So the numerator multiplies, I get square root 3 times square root 3, which is square root 9, which is 3, over 3 times 3 is 9. So that denominator simplifies to 1 minus 3/9. 1 minus 3/9, this would be 9/9. 9, 8, 7, 6. 6/9, which is 2/3. I have a feeling we're going to do something with that. So I'm actually going to move it. Sorry, hold on. I should have done something different. So many backwards. There we go. This is the same as 9 over 9. 9 minus 3 is 6. 2/3. All right, numerator. First, square root 3 over 3. Outer, square root 9 over 9. Inner, and last. Okay, collect like terms. I collect these two. I have 2 root 3 over 3. And if I collect these two, it's going to be 9 over 9, 9, 10, 11, 12. 12 over 9, right? Let's see, what else can I do? I can make that numerator over 9. So this right here gives me 6 root 3 over 9 plus 12 over 9. I'm probably not doing this the most efficiently, am I? That gives me 6 root 3 plus 12 over 9 over 2/3. Remember, division of fractions is multiply of the reciprocal. So 6 root 3 plus 12 over 9 times 3, that's a 3, halves. All right, let's see. I can cancel that. And that would give me, let's see, 6 root 3 plus 12 over 3 times 2 is 6, but I can factor a 6 out of that numerator. Root 3 plus 2 over 6. So my final answer is root 3 plus 2. I am certain there's probably an easier way to do that algebra. I just didn't. I missed it. So we did a nice little review of our algebra skills. But that right there is our answer, as messy as it was. Took way more work than it should have. Last guided practice. Cosine pi over 12. Okay, those are our options, right? That's how we have 12. So if I think about it, if I subtract these two in the right order, I would get pi over 12. So really this is cosine of 3 pi over 12 minus 2 pi over 12. Now, we're certainly not going to use the pi over 12s in our problem. So cosine of pi over 12 is equal to cosine pi over 4 minus pi over 6. If I go back to my formula sheet, the difference of cosines right there is cosine A, cosine B, minus sine A, sine B. Go back to your special triangles, and I know that cosine of pi over 4 is adjacent over hypotenuse, so 1 over root 2. Cosine pi over 6, that is 30 degrees, so adjacent over hypotenuse, square root 3 over 2, minus sine of pi over 4, so it's opposite over hypotenuse, 1 over root 2, and sine of pi over 6, which is 30 degrees, so is opposite over hypotenuse, which is 1/2. Multiply across, square root 3 over 2 root 2 minus 1 over 2 root 2. Rationalize. Can multiply the whole thing. That gives me square root 6 over 4 minus square root 2 over 4. Or square root 6 minus square root 2 all over 4. Cool. Check my answer. And we're good. Nice job. Nope, I just found a mistake. If I look at my formula, this is all good, but when I use it, this is actually a plus, which is a plus, which is a plus, which is a plus, which is a plus. There's my right answer. Whew, good job. All right, some guided practice, our last guided practice problem. Okay, so find sine of A minus B, given that sine A is 18 over 7 in the right quadrant. So we're going to do A is 0 to pi over 2. And then B is going to be between pi and 3 pi over 2 in that quadrant. So if I look at my if I look at my triangle, if this is A, sine, so it's opposite over hypotenuse, so 8 over 17, and then down here is negative 24 over 25. Cosine is adjacent over hypotenuse, so 24 over 25, that is negative. And I'm going to solve my triangle with Pythagorean theorem. All right, there we go. I solved my triangles. Now we're going to find sine A minus B. So I need my formula. Sine of A minus B is equal to sine A cosine B minus, hold on, I lost my formula. There we go. Sine A cosine B minus cosine A sine B. No, you don't have to have these memorized if you're wondering that already. So let's go ahead and plug in what we know. Sine A, I don't need to write that. A was in red, so cos, opposite over, so is opposite over hypotenuse. So 8 over 17. Cosine B, so cos, adjacent over hypotenuse. Negative 24 over 25 minus cosine A, so adjacent over hypotenuse, 15 over 17. I don't know why that one looks like a 15 over 17 times sine B, so opposite over hypotenuse, negative 7 over 25. Do some fancy math, okay? Carry your fractions, watch your fractions, certainly don't get those confused. And I have an answer of messy answer, and these are all going to be messies, and I want them in fractions, right? Okay, because that's an exact answer. If we put it in decimals, we'd be rounding it, which is not good. All right, cool. Moving on. Now we are simplifying expressions, okay? I'm going to take my formula and use the sum formula for cosine to try to simplify things, right? So I have A and B. Cosine A plus B is cosine A, cosine B minus sine A, sine B. And that's 180, which is here. I know that sine is my y value and cosine is my x value. And this is going to be negative 1, 0. So cosine x I can't do anything with, but cosine pi is negative 1 minus sine x sticks around, sine pi is 0. So simplify this, I get just basic old negative cosine x. Okay, so let's try this one. Solve the trig equation for the unit circle. So I have sine x plus pi over 3, sine x minus pi over 3 equals 1. So first let's deal with this part. If I use my sum formula, I get sine x cosine pi over 3 plus cosine x sine pi over 3. So that's this right here. I guess I'll do this one in blue. So I'm adding the difference formula, which is going to be sine x cosine pi over 3 minus cosine x sine pi over 3 equals 1. Okay, go to your unit circle, right? I have on the left, this right here is 1/2. So 1/2 sine x, and this right here is square root 3 cosine x. Moving on, cosine pi over 3 is 1/2 sine x minus sine of pi over 3 is square root 3 over 2 cosine x equals 1. Okay, collect like terms, do what you need to do. It looks like I can cancel. 1/2 plus 1/2 is 1. So I get sine x equals 1. I'm looking at this interval right here. So sine to the negative 1 of 1 equals x. Therefore, x equals pi over 2. Did it. That was fun. Daylight hours. So the number h of hours of daylight for Dallas, Texas and Anchorage, Alaska can be approximated by the equations below, where t is the time in days and t equals 0 represents January 1st. On which days of the year will the two cities have the same amount of daylight? So where are they equal, right? I have two equations. when are those equations equal? That's exactly what we're doing. So let's set them equal to each other. I'm setting h1 equal to h2. So I have 2 sine pi t over 182 minus 1.35 plus 12.1 equals negative 6 cosine pi t over 182 plus 12.1. Sorry, that was so messy. 12.1. All right, let's simplify it a little bit. Let's see. These cancel. If I divide both sides by 2, it looks like I get sine of pi t over 182 minus 1.35 equals negative 3 cosine pi t over 182. Okay, let's move all of that to one side of the equal sign. Well, let's do this first. Right here I have sine of A minus B. So let's actually tackle that first. I know it's not as pretty, but sine of A minus B is sine A. Sorry, 182 cosine 1.35 minus cosine A sine B. Let's just set that equal to the right side for now. All right, crunch some numbers. The B value is a constant, so I can actually take the sine or cosine of it. So the cosine of 1.35 is 0.219. If you hear huffing in the background, that's my dog. All right, so that's where we are. I keep writing that right side down. Cool. All right, let's see, what can I do? I can actually move this to the right. I'm going to write it correctly this time. So I'm going to collect that. That's going to be equal to this, 0.219 sine pi t over 1. Oh, that's awful. And I need a new slide. So I'm transferring that bottom line to a new slide, but I'm going to collect these like terms. Okay, so I'm going to rewrite it with those collected. So I have 0.219 sine pi t over 182 is equal to negative 2.024 cosine pi t over 182. Okay, some crazy math is going to happen. If you remember, tan is sine over cosine. So I'm actually going to put sine over cosine. And who knew? Like, this is just me trying stuff. So I'm moving that over by dividing by both sides. And then I'm actually going to move this over by dividing by both sides. So as crazy as that looks, that gives me tan pi t over 182 is equal to negative 9.242. And now I can actually solve it. So tan to the negative 1 of negative 9.242 is equal to pi t over 182. So pi t over 182 is approximately equal to negative 1.463. I don't know why there's a squiggly at the end of that 4. Cool. This is a cycle though, so it actually, we have to add that whole n pi to it, which is the crazy part that we're learning that I don't expect you to know just because you know. Because it's a cycle, right? It occurs over and over and over again. So we have that n pi. Right now, I'm going to multiply by 182 over pi to cancel those out. Multiply by 182 over pi. That gives me negative 84.76 plus, that cancels, 182n is equal to t, right? I know that's messy as anything, but that means that that's our answer. But let's go back and read the question. It says find the days within 1 year, which is 365 days, for which Dallas and Anchorage will have the same amount of daylight. Okay, so find the days within 1 year that they're going to have the same amount of daylight. So right now I have negative 84.76 plus 182n. If n equals 1, I get about 97, which if you look at a calendar, 30 days, January, February, March, April, that's about April 8th. And then we have negative 84.76 plus 182 times 2, because this happens if we're 365 days. So if we multiply by 1, that's 182 days. If we multiply by 2, that is 8 times 8, 364. We're still within that 365 range. So this is going to be about 279 days, which if you look in calendar, that is October 7th. Okay, that problem was tough and very long. I hope you persevered and watched the whole thing. All right, guided practice. Simplify the equation. I'm not going to go over one of these again in the video, but this is A and B, and we're going to use the sum formula, and it all simplifies to sine x. Right, cosine, this is a difference formula, A and B, and that all simplifies to cosine x. And then A and B, and this simplifies to just plain old tan x. And not that I'd love to do another one, but I would love, if you want to get a bonus point on your last assessment, if you go ahead and show me all the work for this, your answer is about 5.65. Okay, that's a tough one, but if you work through it and show me your work, I would totally do that for you.